Welcome back to this NPTEL online lecture on the molecular rearrangement and reactive intermediates. So in the previous class I started talking about free radicals, and in the today's class I am going to talk about the different method for the generation of free radical and different name reaction. So in the class I am going to talk about first the diverse method for the generation of free radicals. Then I am going to talk about various different name reaction like the Barton-McCombie radical decarboxylation, then Barton-McCombie radical deoxygenation. Then there will be Hans-Dicker reaction, the whole Ziegler bromination, okay, and then there will be several variation of the Hans-Dicker reaction which I am going to also explain in the class. So let's start talking about the radical which I think started talking about in the last class. So first thing I start talking about that there will be a homolytic cleavage of the bonds, and as I mentioned, this homolytic cleavage actually depends on the several factors. It can depend on the electronegativity, the polarizability of the bonds, okay, and then several other effects also very important for the formation of this type of free radicals. So now we are going to understand that there are heat, light or irradiation. I mean, that means all these different conditions, mostly you can see there are heat and light. So it could be a thermolysis, which is mean you are giving heat so that the bond which are the weaker one which is getting cleaved to form the radical. There could be a radiation or photolysis using the UV light, which can also able to cleave those bonds to generate radicals. And then I am going to also include the photoredox chemistry, which is the the recent chemistry using a visible light. Can you do the redox system which can use as a catalytic amount to generate a free radical in the reaction, okay. So first thing I am going to talk about thermolysis. I think you are going to see that in thermolysis, under heat, what is going to happen? The compound can absorb heat and there will be a cleavage of this weak bond here. You can see this is the bond which is the weakest bond in this dialkyl peroxide. Under heat, the two oxygen going to take single electron to form this species, okay. And then under heat, the other compound called AIBN, okay. So it's a azo-bis isobutyl-nitrile. So this azo-bis isobutyl-nitrile was the compound where under heat it is going to actually is going to get out as an N2. So to form N2 you have to take a single electron from this bond and single electron from this bond. This will end up generating this corresponding radical. And this is the radical is very stable radical, so that it can do some other things in the reaction. And you can see why I am saying, because this is again a electrophilic radical, because there is a cyano group here attached to it, okay. So now there are some reaction you can take some of this carbon compound, then under the UV light it can also able to generate this type of acyl radical. So we are going to also talk about some of the generation of the acyl radical, and there there are some of the reactions. And then as I was telling, using some sort of a metal like this, the sodium, magnesium, tin and samarium, that can also use this type of they can also give you a electron. So they can give you electron for this type of reduction reaction. You guys must have heard about acylon condensation, and then several reaction of formation of pinnacle using magnesium. Then some of the chemistry using samarium, where it can generate the radical, it can form pinnacle, and then it can also add to the olefin. So there are several different reactions we are going to discuss about samarium also. And also I am going to talk about some of the photoredox system using the photoredox catalyst as well. In this particular class I am going to focus on this decarboxylation reaction. So the reaction mostly under photochemical and thermal. That means there are some photochemical reaction and the thermal reaction which goes by thermal pathway for generating radical. I am going to discuss them first. So here I am going to start with these three different reactions. As I mentioned, the Barton-McCombie the decarboxylation reaction, where what is happening from carboxylic acid you can generate this R dot, this this type of radical, and then using the Hans-Dicker reaction also from carboxylic acid you will be generating this R dot, which can able to take a proton, which can take a H dot. So there will be hydrogen atom abstraction to form the corresponding RH, or it can participate some sort of intramolecular reaction as well. And then also I am going to talk about the Barton deoxygenation reaction. So starting from this corresponding corresponding alcohol, you can make a derivative of alcohol, and then under H nu or heat you can able to generate corresponding radical. Again this radical can go for a hydrogen atom abstraction from the RH, or it can go for a intramolecular cyclization reaction. So first thing is the Barton-McCombie decarboxylation reaction. So here you can see the carboxylic acid is getting converted to the corresponding acid chloride using thionyl chloride. And then once you use this N-hydroxypyridine 2-thione, so this is a N-hydroxypyridine 2-thione, that sodium salt of it, once treated with here, Now this O minus here can attack here to this corresponding acid chloride, get rid of the Cl to form this type of thiohydromate ester. Now this thiohydromate ester going to participate in a decarboxylation reaction in the presence of tributyl tin hydride and AIBN in place of benzene and heat. So what is happening? It's this R is becoming R dot to form this RH, and then there will be formation of the CO2, and then you will see this 2-tributyl stenyl thiopyridine, which will be a byproduct going to form. Okay. So now we are going to learn about the mechanism of the Barton-McCombie decarboxylation reaction. First thing is the initiation step, where the AIBN going to get decompose in presence of heat to generate this radical and N2. So now what is going to happen? This radical can take the another weak bond getting clipped between the tin and the hydrogen. So now it is going to generate this type this radical can cleave this bond to generate the tributyl tin radical here. The tributyl tin radical can now interact with this carbon sulfur double bond. So that bond is getting cleaved to generate generate a radical next to nitrogen, which is going to form a bond here, and it is going to allow this cleavage of this nitrogen oxygen bond. Okay, so what is happening in after this stage? You are generating this type of radical species. So you are generating this one, and now you can see you are generating this N dot, then there is a S, SN, BU3. So there is a dot here. So finally they are forming a bond to generate this corresponding. So this can go to the forming this compound, 2-tributyl stenyl thiopyridine, and then this one going to happen go for a decarboxylation to get rid of the CO2 to generate a R dot. Okay, so it will form this R will form a R dot, which will abstract a hydrogen from this tributyl tin hydride to generate this RH. Okay. So now we will see some of the example here. In this compound, you can see there is a EWH here. Under this type of Barton-McCombie decarboxylation condition, what is going to happen? It is going to generate. So you can form this type of ester species here, which can generate this type of radical. Now under if you have oxygen here, as I mentioned, it can give the electron to the oxygen to form these compounds, which can able to abstract after the reactive workup. It can form the corresponding alcohol. After that, it can be converted to this compound after few steps. Okay, so that means you can not only get to H, you can also convert to corresponding OH. So here is another interesting example. Here you can see you have this bis thiohydroxymate ester. So that means you have both sides. This is a dicarboxylic acid. From this dicarboxylic acid, you can able to make this compound, as I mentioned, from make corresponding acid chloride, and then you take this corresponding sodium salt, or you can take amide coupling reagent to make this. Now what is happening under this H nu and DCM, and if you take this tetraconic anhydride, it is forming a radical and it is going for a 1,4 addition. Once this radical is adding here, this is actually it is generating another radical in this position, which is you can see it is a tertiary radical. At the same time, this next to a carbonyl group here, it is getting stabilized. So what is going to happen? It can also interact this radical which is forming in the reaction. Okay, so it can interact with this radical to form this species. That means you can see there is a difunctionalization happening of this olefin, and then under room temperature there is a elimination happening of this group. Okay, so it can eliminate to form this corresponding olefin here to get to this compound. Okay, there is another example here. So you have a 2-carboxylic acid here, which can first form this corresponding hydroxymic ester first, and then using this condition, after the associated to form the corresponding acid chloride, then the corresponding thiohydroxymate ester, and then finally it is abstracting the hydrogen from here corresponding thiol to get to the cubene. There are another example here. So this is exam question, that if you start with this carboxylic acid and then what will be your A, what will be your B. If you use the tributyl tin D, like instead of the hydrogen, there will be a deuterium abstraction going to happen. So I think I have already discussed that you end up getting to this. This will be your A. That means under this amide coupling condition, you are going to end up making this compound, and then once you use tributyl tin hydride, it is going to cleave here. So there will be decarboxylation going to happen, and then it is going to abstract this tin and the deuterium bond getting cleaved to introduce the deuterium here. So that will be your B. Now I am going to talk about the other important reaction is Barton-McCombie, the radical deoxygenation. So we talk about the decarboxylation. Now we are starting from the corresponding alcohol. So if you start from corresponding alcohol using this R double bond HCl, using this compound, what you can do, you can able to convert to corresponding thioxoester. It will form the corresponding thioxoester under the tributyl hydrate and AIBN in a reflux condition. It can replace this corresponding OH2 by H. So that is going to happen, a deoxygenation happening. Okay. So now what is happening? The hindered tertiary and secondary alcohols are also compatible here. Okay. So this is what is happening. It is some sort of a way you are converting this corresponding OH to corresponding RH. Okay, OH to RH. So we are going to understand the mechanism here. What is happening? First step is the initiation. That is the AIBN is getting decomposed to generate this radical. After the expulsion of the N2, it is the cleaving this tene hydrogen bond to generate this tributyl tene radical, which can again very similar to the other reaction here. The decarboxylation reaction here is very similarly interacting here with this carbon sulfur double bond to generate a radical species here. Now it is going to allow you to cleave this this carbon oxygen bond is getting cleaved to generate a radical, and at the same time you are making this tributyl tene xanthate. Okay, because this you are forming a carbon oxygen double bond, and at the same time you are formatting this tertiary radical, which is going to abstract a proton from the tributyl tene hydride to generate this corresponding species. Okay. So here are some examples that so this chemistry can be applied in the natural product synthesis. You can see here, you can see at the beginning what is happening. You have this carbonyl group. So what actually happening from the starting from the product, you want to replace this carbonyl group by a hydrogen. So what you will do? So if you know that you have a carbonyl group, you can of course go for some other reaction. I am sure you know how to convert the carbonyl to the corresponding CH2. Okay, but we can do for also other approach. Okay, we can also convert the carbonyl to the corresponding alcohol first, and then corresponding alcohol to we can make these thioxoesters under this the Barton-McCombie condition, and then we can use the tributyl tene hydride and the AIBN. Okay, so that is going to do the job to convert this corresponding CO to the corresponding H. Okay, and you have another CO group which is in the protected form. So you can now able to open up in place of a HCl to open that. Okay, and then you can use the the Wittig condition to introduce the olefin here. Okay. So there is another example here. You can see you have this alcohol here. So which is under the Barton-McCombie condition, which generate the thioxoesters, and which can using tributyl tene hydride and AIBN it can form this compound called kisi-lactam to convert this OH to the corresponding H. Okay. There is another very interesting example. This is very important because why I am saying this is very important, because this particular chemistry of this Barton-McCombie the radical deoxygenation actually used for the synthesis of one of the key intermediate of agar diractine. So it's a very important natural product from the neem tree, which was synthesized by Steve group in Cambridge. So in their synthesis, what they found that one of the important steps they have actually from this alcohol they have generated this thioxoester, and then using the AIBN and tributyl tene hydride they generate this radical, but this radical took part in an intramolecular cyclization. As I mentioned that this radical fate is not always going to this corresponding H, it can also participate in an intramolecular reaction. So that is happening here. It is attacking here, participating in an intramolecular cyclization reaction between this allene and this radical can end up making this type of products here. Okay. So there is another very interesting example of this Barton-McCombie radical deoxygenation reaction. Again you can see first this thioxoester is formed from the corresponding alcohol, and now under this Barton-McCombie condition what is happening? First it is forming this radical. Once it is forming this radical, now you can see there is a cyclopropane ring here. Okay, so now that ring is getting chopped here, formation of a radical here and here to generate this type of species. So you can see this entire things becoming another pyridine ring here at the end of the day. Okay, and this now at the end it is generating one radical here to generate this species, and finally it can able to take a hydrogen from the tributyl tene hydride to get to this type of species. So now I am going to talk about the Hans-Dicker reaction here. In 1963, the Hans-Dicker reported when dry silver salt of aliphatic carboxylic acid was treated with bromine, the corresponding 1 carbon shorter alkyl bromide was formed. So it's a very important reaction because you started from this corresponding carboxylic acid, and your carboxylic acid actually gone. This part goes for a decarboxylation, and you instead of this the Barton-McCombie reaction, here you end up getting X. That means you can take a halogen. Means from you starting from the corresponding acid, you can synthesize a corresponding alkyl halide, okay, using a silver salt, okay. So here what is happening, this reaction can be done with silver, thallium and mercury. So it is forming the dry silver salt first, and then once you treat with the corresponding halogen source in terms of dry solvent in the reflux, it is forming the acyl hypohalite. So once it is forming the hypohalite, then after that it is forming the CO2 and then corresponding Rx. So you can see mechanistically after this what is happening, this minus is attacking to the X, forming this hypohalite, and then there will be cleavage happening between the O and the halogen bond. This is a weaker bond here to generate X dot, and after that once you know that you are generating this species, it will be not going to stay there, it will immediately go for generating a free radical. At the same time a CO2 will be expelled from here to generate this R dot, which now going to take a X dot from here from X2 to generate Rx. So again there is a mechanism given here. Once you have this silver salt of this type of benzyl acetic acid, first this formation of the hypohalite, then under H nu or heat it will generate this species here, which can participate in a decarboxylation to generate this benzyl radical, which will take the bromine from here to generate this corresponding benzyl bromide. There is a modified version of this reaction. So this is called the modified analytical reaction or the crystal Frith modification. So what is happening here in this reaction, they are using starting from the carboxylic acid, using the mercuric oxide excess, or they are using the CCl4 and or the DC and X2. Okay, that means these are the conditions. So instead of the silver, now so these are the different variation actually developed. So I think the most important thing is from here to here the corresponding hypohalite. So this is the development happen, how to form the hypohalite in a different route, because once you generate the hypohalite, now this is going to under H nu or heat, it is going to generate this corresponding product. Okay, so it is actually a one-pot reaction of excess red mercury oxide and one equivalent of halogen. So now I can give you some Barton modification. So Barton modification of this reaction. So what is happening here? First, starting from this corresponding carboxylic acid, it is actually forming this acid chloride, then forming this hydroxamide ester. So now I think if you see in the Barton decarboxylation reaction, we know it is forming the R dot, correct? Just because there is a tributyl tin hydride at the end, that's why the reaction is going from formation of the RH. But now if you are able to bring this some sort of a XCOI3 where the X can be transferred, then you can able to synthesize corresponding Rx. So that is happening here. Once you have a CCl4 once you have some other species here, that R dot can able to abstract the corresponding chlorine or bromine to form the Rx, and then the corresponding CCl3 dot or the CBr3 or so, which can further goes back to the system. Okay. It can also actually what is happening once you form the CCl3, it is actually interacting with this to generate this corresponding SCCl3 species. So what is happening? It's very similar to the tributyl tin hydride, where the tributyl tin actually at the end attached with the sulfur. Here you have this CCl3 which is actually attached here. So there is a modified some of the other modification using the the xenon fluoride using HF. Again I think there is a formation of this xenon ester here. As I mentioned, once you form there, it is going to cleave the bond, formation of that species which is going to form the R dot. Okay. Again you can see once you have R dot, it can able to get if you use that tributyl OX, it could be X, could be halide, then it is going to abstract this this halogen to form the corresponding Rx. So there is a Cauchy modification here using the the lead tetraacetate, the X2 lead tetraacetate carbon tetrachloride reflux. What is happening again, the lead tetraacetate is forming this type of lead diacetate at the end, formation of the Rx. Again it is happening this corresponding to lead tetraacetate reacting with this acid, and then after that you are actually there is a formation of this the very similar type of reactivity, that at the end it will be formation of the R dot, and then it will take a X corresponding MX source, and then the Cl will be transferred to make the corresponding Rx. I think it's a detailed mechanism is given here, how this is formation happening. So it's a lead tetraacetate going to react with the carboxylic acid, as I mentioned, to form this type of species, which can under heat it's going to generate the R dot, which can finally take the X from corresponding MX. So here are some of the application of the Hans-Dicker reaction. There are several applications. We have just bring some of this example here. If you have this bicyclic 1,2 diacid, then this bicyclic diacid can form this corresponding bromide here, which can be trapped with this type of species to make some sort of a trap and strain cyclopropane. Okay, you can see you have this cyclopropane already there. Now this 2-bromine can be trapped with this species to form this type of trapped cyclopropane. And then there is another example here. You can see starting from this carboxylic acid, using the silver bromide and heat, it is the original condition. You can make corresponding bromide here. Then the final one for this class is the whole Ziegler bromination. So what is happening? I think we all know that if you have a olefin, if there is a allylic position here, then this allylic hydrogen can be abstracted and can be replaced with a bromine if you do allylic bromination. Okay, so this was discovered by the Wohl and Ziegler in 19 and 1942. Here they have used the NBS and CCl4 under reflux to get to this corresponding cyclohexene to the 3-bromocyclohexene. So this reaction called the allylic bromination, and currently this reaction can be done with the visible light instead of this using the UV light. So what is happening here? If you take the alkane and the NBS, and if you give a radical initiator, it can end up making to the corresponding allylic bromide. So from allylic, from corresponding alkyl benzene, if you have a benzylic position here, it can end up making to the corresponding benzylic bromide. Okay, so this is a very good method if you want to make a benzylic bromide, okay, or a allylic bromide as well. So I think the first thing is you have to use a initiator. That means if you have this benzoylic hydroperoxide, so what is going to happen? This peroxide going to cleave, and then it's going to form this species. As I said, once you are forming this species, you can generate this pH dot here. And now at the same time, what is happening? The pH dot can interact with this Br2 to form this Br dot. Okay. So now this the Br dot is the one which is the active species, which is going to abstract this carbon hydrogen, which is going to cleave this carbon hydrogen bond to generate a radical which is a 2 degree and allylic. Okay. Now once you have this allylic radical, it can interact with this bromine, okay, to form this allylic bromide. So there, once you form the bromine, there will be radical chain termination happening to form this corresponding allylic bromide. So there are some of the application here, starting from this corresponding, indoles. If you have a 3-methyl indoles, then using the NBS and AIBN under CCl4 reflux, you can make this corresponding. So now this, now this benzylic position will be, brominated, which can be able to, finally after some step can able to make to this corresponding, trifluorostatin A. So you can have another example here. You have a methyl group which is a benzylic position. It can form this corresponding benzylic bromide, which can be converted to a bioactive compound. Okay. So in the today's class, we have learned about the Barton-McCombie decarboxylation reaction. You have learned about the Barton-McCombie deoxygenation reaction. You have learned about the Hans-Dicker reaction, the whole Ziegler bromination, and I am sure there are more reaction of the radical chemistry, which I am going to bring to the next class. Again, there are very similar textbook. You can follow this topic, and then thank you all for coming to the class, and I am sure you are going to come back to the next class. Thank you.